Hello everyone, this is Yuhu. Today I'd like to talk about using automatic bug injection tools to characterize and improve bug finders, especially for KLEE. Firstly, I'd like to do a quick introduction about Lava. Lava is an automatic bug injection tool which can inject bugs into C programs. Lava can control the type and location of bug and also the number of injections. Each bug is validated to be triggered by a special figure input. With Lava, we can create a vulnerability corpus, a dataset of bugs on demand. With this one choose vulnerability corpus, we are interested in the following questions. When might KLEE miss a bug? It also means when KLEE may raise a false negative result. This is the most important research question in this presentation. The remaining questions are more practical. We will discuss them later. Firstly, to answer the question when KLEE might miss a bug, we have a two-stage analysis, small program analysis and a real program analysis. In a small program analysis, we expect that KLEE can traverse all possible paths and should be able to find any bug we injected. In other words, if it misses a bug, this indicates a soundness issue. In a real program analysis, we evaluated KLEE with the real programs with Lava bugs to test KLEE with a much more complex target and environment. Our target small program is toy.c, whose input is a binary file and output is the meta information. We generated 159 buggy programs. Each program only contains only one injected bug. We ran KLEE with these buggy programs with enough time and enough resource, and we confirm that all experiments are exited normally without any state drop. Here are our evaluation results. We tested both KLEE version 2.2 and KLEE version 1.4, since we know many researches and projects are based on KLEE version 1, such as AEG, S2E, and ZST. From this result, we found KLEE version 2 has a significant improvement of KLEE version 1. Let's focus on the user-defined function. KLEE missed 4 bugs because the trigger value was used as a floating point. When KLEE encounters a symbolic value used as a floating point, it concretizes the symbolic data to the constant 0. We are also interested in why KLEE version 1 missed too many bugs with the printf function. First, KLEE uselibc does not include printf by default. Enable printf and compile time will allow KLEE version 1 to detect an additional 31 bugs. Then when we investigated the remaining missed bug, we found they all injected into the first parameter of the printf function. Here is an example code about the buggy printf function. Lava injected an overflow at the first parameter of printf function. It will be triggered with a special figure input. The cause of these misses is that KLEE version 1 does not check pointers passed to external library calls for validity. There are good reasons for this. In some cases, pointer values passed to functions are not expected to point to a valid object. As long as the called function does not dereference the pointer, this will not result in a runtime error, and raising an alarm would be considered a false positive. And we also found KLEE version 2 solved this problem. Now, let's move to real program analysis. When might KLEE miss a bug with a real program? The first possible answer is path explosion, so it's hard to distinguish false negatives caused by resource limitations or unimplemented problem. To solve this problem, we introduce Concolic execution in our evaluation. We note that KLEE has its own Concolic mode, known as seed mode, and also S2E and ZST provides their Concolic mode. But our purpose of the Concolic execution is a little different with these tools. So we modify KLEE to develop our own Concolic KLEE. We ran KLEE twice. First run with a concrete input and record every branch encountered and the log information, such as the program counter, branch conditions, and the source code line. Because we are interested in running KLEE with symbolic input, we then rerun KLEE with symbolic input and guide KLEE to follow the concrete trace to the injected bug. If Concolic KLEE misses the bug, meaning that KLEE's environment model or execution were not sufficient to uncover the bug. Here is our result. We selected 200 bugs with unique tag points. Now, our research question was changed to, why did the Concolic KLEE miss these bugs? For example, KLEE and Concolic KLEE only found 5 out of 119 bugs injected into Who program. We found the missed bugs are caused by the diversity between the glibc and the uclibc. For example, uclibc doesn't have header file libio.h. In addition, the two standard library implementations may have the same API but use different data structures to implement things. Here is one example. The structures have the same name but with different data structures. To determine this problem, we use the uclibc to compile our buggy programs and run the given concrete triggered input to check if the bug can be triggered in the uclibc environment. Some of the buggy programs can't be compiled with uclibc, since the injected bugs have a glibc structure, but the uclibc doesn't have the definition of these structures. We found that the result of Concolic KLEE matched the number of correct triggered bugs with uclibc, which means if the injected bug can be triggered correctly, Concolic KLEE is able to find them all. For the remaining research questions, we are interested in the effect of symbolic file size, searching strategies, line coverage, and depth of the injected bugs. And the following results are all based on our base64 experiments. Since base64 processed 4 bytes of the input file at a time, we can see that with only 2-byte files, none of lava's bugs can be found. With 4 bytes or more of symbolic file data, KLEE found the majority of the bugs. However, at large file sizes, KLEE in some cases finds few bugs. At 512 bytes, KLEE found only 18 bugs, and with 2048 bytes, KLEE only found 1 bug in 50 hours. These results indicate that the execution time and the symbolic file size should be carefully tuned for the specific program. For the next question about searching heuristics, it's worth mentioning that the injected bugs of lava were constructed with 2 functions, lavaset and lavagate. To trigger a lava bug, the program must execute the pair of lavaset and lavagate functions in that order. So different search heuristics will result in a significant difference in the number of executed states from lavaset and lavagate. For instance, BFS may never reach the lavagate because BFS solves all possible states between the lavaset and lavagate. The states may exceed the memory camp and result in the termination of the states. In our experiment, we tested various single search heuristics as well as several combinations of these heuristics. We found random path selection outperformed the other methods. An interesting finding of interleaved strategy is the performance of the interleaved searching strategies is based on the best single searching heuristics, except the random state searching. For example, KLEE identified 8 bugs with DFS, but with interleaved with the random path selection, KLEE could find 22 bugs with a different order and time cost. It's the same situation when IPS combined with a non-uniform random search. We also found a counterexample, which is random state search. It might be caused by the construction of lava bugs. A direct and straightforward limitation of KLEE's performance and bug finding is coverage. If KLEE cannot execute the line that contains a bug, KLEE obviously can't find it. In our base64 experiment, we found that KLEE could cover more than 80% of total covered instructions in less than 1 minute, but continued running for a long time without any further increases. From this experiment, we found although the line coverage bounds the maximum number of bugs found, for example, the last bug shown in this figure. But it is not directly correlated to the bug finding performance. This implies that in many cases, we cannot claim bug finding performance depends on line coverage measurements alone. It is generally understood that deep bugs are difficult to find. One important point is that measuring the depth of bug is not as simple as computing the distance from the start of the program to the point where a bug manifests with lava bug. To validate this intuition, we examine the correlation between several different notions of depth and how much time was required to find the bug. Firstly, we used a perf to measure the number of executed instructions. The results shows that KLEE found all 21 shallow bugs, and only 1 out of 7 deep bugs. Although Lava provides a triggering test case, the path taken by the program for this input may not be the shortest path to the bug. In our experiment, we found KLEE sometimes found a different path to the crash. Hence, simply measuring the number of instructions executed dynamically may overestimate the depth of a bug. To get a more accurate notion of the depth of a bug, we have 2 ways of measuring depth. Static analysis of the shortest path from the start point to the lava set and then to the lava gate, and a dynamic unique basic block count. Our results seem to show it's linear with R square equal to 0.52 or degree 2 polynomial regression with R square equal to 0.53 with these 2 notions. This result is surprising, because we expected the discovery time to be exponential in depth. However, this may be due to not including enough deep bugs in the evaluation. In conclusion, our small program analysis section, we describe the soundness problem about the floating point and the printf function call in KLEE version 1. In our real program analysis, we tested a different configuration with KLEE to evaluate the real program. In addition, in our Concolic KLEE part, our main finding is the diversity between glibc and uclibc can cause KLEE to miss some bugs or report errors that are hard to reproduce. So our experiments prove that automatically generated bugs can really help to understand, evaluate, and improve bug finding tools. Thank you.